Well, hello, my name is Marcel Guim and I am partnered with Clara Ruiz. We're both from the 3D group from CSD. And we've been tasked with doing a comparator from 60 bits using the int, so we can differentiate between positive and negative numbers. And to do this, we've been using these schematics. So as you can see, we have 4 different 4-bit comparators, which are chained. So the output we get from chip 1 is automatically sent as an input to chip 2. The same goes with chip 3 and 4. And this way, we are going to get 3 different outputs, GT, EQ, and LT, which are going to tell us if A is higher than B, or B is equal to A, or B is higher than A. As you can see in this truth table, we have here in red, when A is higher than B, it doesn't really matter what GI, AI, and LI is. So we're going to obtain A100, meaning that A is higher than B, because G greater than is the one activated. If A is smaller than B, independently of the outputs GI, AI, and LI, we are going to get 1 at the LT, meaning A is lower than B. If A equals B, then we're going to obtain a 0, 1, 0, which is going to be based on the input that we get on the first time. And if we get some other values, it's not going to matter because it's not what we have expected, so we don't really care. If you let me turn this board, I can show you how we made the 4 bits and 1 bit. So as you know, when doing this VIZL file, we don't have just one file, we have a total of 5. Going from the 16 bits that I just showed you, which is chaining 4 different comparators for 1 bit, for 4 bits, sorry, and this 4-bit comparator is also chaining 4 different comparators from 1 bit this time. And then this 1-bit comparator is going to be chaining a decoder from 5 to 32 bits, which is going to be chaining 2 different decoders from 4 to 16 bits. As you can see here, this schematic we have for the COM4 bits, it's the exact same one we had for the 16, but instead of using COM4 bits inside of it, we're using COM1 bit. This way, if we sum them, we get 4 bits. And it's the exact same thing we talked about before. So we get some outputs from the first chip, which we send to the second one, third, and fourth. And the truth table for this comparator, it's the exact same one, meaning that for the chip 4, for example, if A is greater than B, we get GT equals 1. If A is smaller than B, we get LT equals 1. If A equals B in this 4 chip, GI, AI, and LI are going to be the ones that are going to set the output, meaning that if A equals B and GI is 1, EI and LI are both 0, the output we get from the chip 3 is that A is higher than B. So this will generate the same output, as you can see here. If we are getting that the previous comparator gave us that they're both equal numbers, we are going to get equal numbers. And if it's the opposite, meaning that B on the chip before, B is smaller than, bigger than A, sorry, we are going to get the exact same thing. B is greater than A. In this comparator for 1 bit, we haven't yet planned, the decoders, so you're going to see that next, shown by Clara. But as you can see, we have the same ones, so A and B, this time are just 1 bit each, and GI, AI, and LI are some 1 bits too. So we get the same results, GT, EQ, LT, which we use them for the comparator 4 bits. And that's it.
So, the comparator of 1 bit is made out of one decoder of 532 bits, which is made out of 2 decoders of 4 to 16 bits. So, first of all, we're going to explain the logic circuit that goes before the decoders 4 to 16. It has 2 outputs, 2 main outputs. The E, which means enabled, so if it's 1, the circuit will function, and if it's 0, it won't. And G4. If we input a 0 in G4, the result will be that the first decoder will be functioning, and this one goes from bits 0 to 15. If we input A1, the second decoder will be the one functioning that goes from bits 16 to 31. Therefore, we will be inputting a vector of 4 inputs, 4 bits, that will go to one of these decoders. These decoders, what they will do will be that they will transform the vector to some specific bit that will be the H output. That will go from 0 to 31 in a total of 32 bits. As I said before, the decoder of 532 is made out of 2 decoders of 416. So I'm going to briefly explain this type of decoder. It has 2 different inputs, the E that means enabled, and as I've explained it before, if it's 1, the decoder will function, and if it's 0, it won't, and the T, which is a vector of 4 different inputs. This decoder will have 16 different outputs, which are 16 different Ys. So if the E is 0, as I said before, the decoder won't function. But if it's 1, we'll receive some different outputs, depending on the combination of the vector D. So, for example, if D is 0, 0, 0, 1, we will receive channel Y0.
So now we're going to show you our program. And first of all, we're going to show you the input files that we've used to run the Quartus Prime project. So first of all, we have the decoder 4 to 16 that has 15 different inputs. So for each input, we receive a Y output. Then we have the decoder 5 to 32 that assigns each input from the decoder 4 to 16 to an output. So first of all, we have the 0 to 15 bits and then the 16 to 31. Then we have the comparator 1 bit. This comparator processes all the information given by the decoder to show us the output, which consists in a sum of minterms. After that, we have the comparator 4 bit, which consists in 4 comparators of 1 bit. We have used a new vector such as key, K, P, and Q to send information from one chip to the next one. So therefore, we are assigning these different inputs to an output to use it on the next chip. Finally, we have the int.comp 16-bit, which uses 4 different comparators of 4 bits.
So if we analyze the RTL viewer, as we said before, for this int.comp 16 bits, we are using 4 different comparators for 4 bits. So using summing the 4 bits, we get 16. As you can see, we have chip 1, 2, 3, and 4, which are basically the same, a comparator for 4 bits. So if we open this one, as my partner Clara said, the comparator for bits, it's 4 different 1-bit chains together. So the same thing applies here. Chip 1, 2, 3, and 4 are the same ones. If we open the comparator for 1 bit, we can see that we have a decoder from 5 to 32 bits, plus GT, EQ, and LT, which is the minterms we talked about. Going on to the decoder from 5 to 32, it's 2 different decoders from 4 to 16, which we can see now, and the decoders are made of a total of 15 different muxes, 16 if you count the 0, my bad, and we get 4 inputs and a total of 16 outputs.
Okay, so finally, after having run the Quartus Prime project, we obtain an int.comp 16-bit test bench file that we can input in ModelSim Altera, a software tool that we will use to see if our project works. So first of all, we will input some vectors and compare them with another one to see if they are equal, greater, or lower than. So first of all, we have minus 32,766 compared to 0. So we can see that 0 is greater, so B is lower than A. Same thing happens when we compare 0 to minus 14,600 and minus 12. After inputting a positive vector, which is 18, we can see that the outputs change, and now we have greater 2 at 1, so we can see that A is greater than B. Same thing happens with 27,433. Finally, if we change 0 to minus 32,768 and we compare it with the same number, we obtain that both inputs are equal. So we conclude that our program works as we expect it to. Thanks for watching.